What up, algebra people? Oh, you thought I was going to say squad, sucker. All right, let's get started with today's lesson, 7.1. This one is titled Multiplication Properties of Exponents, all right? Just get in your mind that we're going to be dealing with properties of exponents. How do exponents behave? Hopefully, you guys already understand what exponents are, and those are just the little numbers that are above to the top right of any other number. So right now, this is 5 to the power of 3, right? Or you can call this 5 cubed, 5 cubed. So how does, actually, let's keep it. How do exponents behave? Remember that exponents is repetition of multiplication. 5 to the power of 3 is 5 times 5 times 5. This here would be your answer, all right? Or I'm sorry, you would simplify that doing 5 times 25 and then times 5, and then you can simplify it as much as possible, all right? So with that said, we are going to be dealing with something a little bit more generic, okay? Which is not what I showed you, not only what I showed you, because it's very simplistic. You guys should have already learned how to answer something like that, or 12 to the power of 4, whatever the case may be. But here is going to be a little bit more generic with variables, right? So what you see on the screen right now, this is what we should be learning how to do today. So after today, you should be learning how to answer this one right here, x to the power of 2 times x to the power of 3. You should understand how to answer this one, which is x to the power of 2, and then once again to the power of 3. And then this one over here, which is x to the power of 5 times y to the power of 2, and then all of this raised to the power of 3. So as you can already understand, the parentheses here are very important, and where these exponents are located. All right, very important. So something before we get started as well that's very important to know, where a lot of students trip up. If I were to show you this right here, which is xy to the power of 3, please understand, don't forget, the first thing is that at any time two variables are next to each other, they are multiplying. So I can actually expand it out so it can look like this: x times y to the power of 3. So where was I trying to go with this? I'm trying to let you know that the power of 3 has nothing to do with x. Nothing to do with x. Please understand that the power of 3 belongs to the y. So I can further expand this to look like this. X is actually multiplying not with 2, but with 3 y's. That is the expanded version of this. So please understand that the 3 has nothing to do with the x. Now, if you're telling me that you have this right here, then yes, the 3 does get applied to the x. But we're going to see that in a little bit. So just hold on and let's get working. Now, if you're in my class, you're doing two things. You have a lined piece of paper with you, and you're also working in your book. All right. So what I need you right now is, when I tell you to do something in your book, do it in your book. When I tell you to do something on paper, do it on paper. A lot of the times I might not be reminding you because it might be very obvious. Just get the feel of the lesson. All right. The first thing we want to do is, you're obviously reading this from your book, a monomial. All right. A monomial is a number, a variable, or a product of a number and a variable. And it's only one term. All right, so the term a to the power of 4 is a monomial. Now, I'm not going to keep reading this because this could be very, what you call it, like confusing if you're not a reading person, if you're more of a visual person. What is a monomial? Well, a monomial is a lot of things. Think of any number in the world. It can be positive, negative, it can be a decimal, it doesn't matter. I'm going to put here the number negative 3.5. That right there by itself is a monomial. Now, understand that mono, okay, the prefix mono means one. And what a monomial is only one term, meaning we are not adding anything to it. So I'm going to go ahead and put another thing here. I'm going to put 4x. So this right here would not be a monomial, because monomial will only have one term. This has two terms. It has one term right here and it has another term right here, and a total of two terms. So we're not dealing with, imagine like I always see this as a little train, right? And the addition and subtraction symbols will be the carts. So we're only working with one cart of the train, monomial. Whenever we work with two, then we have binomial, like a bicycle, right? Trinomial will be 3, so on and so forth. But don't worry about the others. We're dealing only with a monomial. Now, what can be a monomial? Mr. Crania just said that it can be the number, this number, negative 3.5. It can be any number. It could also be any variable. So I'm going to put here the variable w. So imagine if I just put w, which represents a number. That could be also a monomial. Or it can be the multiplication combination of the two. So I already told you before that this by itself could be a monomial. That's a monomial. And I can combine them through multiplication. What's negative 3 times 5? Not negative 3 times 5, negative 3.5 times w. Well, it's negative 3.5 w. So these three things separate are monomials, okay? It's just one term, just one out of those wagons from the train. If you're still freaking out, if you're wondering what the heck is a monomial, just remember, imagine writing a long equation, but we're only taking one of those things, only one of those, so we're not looking at any adding or subtracting. We're not adding any more cards or subtracting. So it's just one, okay? Now it does say here, there's a rule for something to be considered a monomial. What is not a monomial? A monomial is when we have a variable in the denominator, okay? We cannot have a variable in the denominator. We will explore that a little bit later. And remember, denominator is division, so we cannot be dividing by a variable. We'll explore these a little bit later, so don't worry about it too much. All right, so the first key concept, the first idea that we're going to be learning about is called product of powers. Whew, here we go, product of powers. Right now, this is where you're making little notes, side notes in your book. I don't want you to write this all over. It's only if you want to. Now, for those of you that want to read, go ahead and pause this and read it right now. But those of you that want the visual idea of it, this is what I'm talking about. We are going to find out what it looks like when you have, and this goes back to the same idea here in our entry slide, right? This is what we're going to be focusing on right now. Okay, so when two terms have, and this is funny because it's not really two terms. I'm not separating this by adding or subtracting. This is actually multiplication. When you are multiplying two things that have the same base, and what do I mean by base? Well, base are the original regular size numbers. And then if they have exponents, what do we do? What does that look like, right? What will this look like? It's very simple. If you go ahead and look what this is right here, when you have the same base number, right? When you have the same base number, all that happens is we are going to keep the base number and our exponents are going to add. And I'll explain that to you in a second. So my answer is going to be whatever m is, whatever it is, and we're going to be adding with n. Now, how does this make sense? Well, let me make it make sense to you using the idea of the first slide, which I believe it looks something like this. I believe I chose something like this. What is x to the third times x to the second power? What is that? Well, if I were to expand this, I'm going to expand it. I'm going to write it in an expanded form. X to the third means that there are 3 x's multiplying together, right? Because exponent means repetition of multiplication. So there's 3 of them. Now, don't forget that we're also multiplying it. We're multiplying this with 2 other x's that are multiplying, right? Power of 2. Right? So hopefully you can agree with me that this right here represents my x to the power of 3, and this one is x to the power of 2. So if you are telling me that we can just grab this bundle and write it like this as x to the third power, and we can grab this bundle and write it like this as x to the second power, well, doesn't that mean that we can grab the entire bundle and write it as x to the 1, 2, 3, 4, 5? We literally just added them all together. That right there is your answer. That is all we're doing. When you have the same base, x and x, and these things are multiplying and they both have exponents, we simply add those exponents. That is it. It's as easy as that. So let's go ahead and see what we have next. In this same page on the right side, there's a question. How does the process for simplifying b to the second power, so b to the second power times b to the fourth power, differ from simplifying b to the second power plus b to the fourth power? Okay, really quick. This right here is not, is a monomial, It is not being separated by adding or subtracting. It is not being separated by adding or subtracting. This one right here is not a monomial. This one is a monomial. This one is not a monomial, because that's one term and that's another term. How come, Mr. C? Why not? Well, because let me explain it to you. I'm going to expand this. B to the second power is 1b times another b. That's what it is. Now, if I grab b to the second power and I multiply it by b to the fourth power, it's going to say, okay, so I'm going to multiply with 4 more b's that are already multiplying as well. That's what it looks like. So this right here is b to the fourth power, which we can grab all of them and just put them under the same base number, b right now, which is b. We have the same base number. So 2 plus 4 gives me a total of 6. 1, 2, 3, 4, 5, 6. Don't think that these are exponents. They're not. So my answer right here is b to the power of 6. Okay. Now, what is the difference here with this? This is called a binomial because it has its two terms. This binomial is a little bit different. Why? Well, you can only see it when you expand it. We have a b, right? We have a b here times another b. And we're adding b to the fourth. So b times b times b times b. So you have this, and then you go, well, what does this do? What, like, how much further can I do after expanding it? The truth is that we don't have the same idea here. Since we're adding, we're adding or subtracting here, we are not able to simplify this that much further. Why is that? Well, we have, or another way that I can show you instead of doing this way, I think another way that's going to be a lot more clear to look at it will be this. Remember that in front of every variable, we can put a 1 if there isn't any number, right? So there it is. And once again, we can put a 1, right? So imagine if there was another idea where it was 3b to the second power. Nothing crazy, right? I'm just going to take it one step further. If we had 3b's to the second power plus, and I want you to look at this one, let's do 2b's to the fourth power. How else can I show this so I can explain to you why you cannot combine this? This cannot go any further than what it already is. It has to stay that way. Well, because if you think about 3b's to the second power, this is what we're doing. B's to the second power, there's one of them. Plus, remember that this number tells you how many of those you have. So we have 1, 2, and now we have a third one. And this is in repetition of addition. Remember that the number here is repetition of addition, and the exponent is repetition of multiplication. Be careful. That is very simple. It's a very simple idea, but very confusing at the same time. So you have that. You have 1, 2, and 3 b's to the second power. And then down here, I'll do it in blue. You have 2 b's to the fourth power. So here's 1, and I'm going to add another one. And here's another one. So the idea is that do you have a total? Do you have a total of 1, 2, 3, 4, 5? Do you have a total of b to the fifth power like that? No, they're not the same variable. Sorry, not the same variable. They are the same variable, but are they like identical variables? The answer would be no, because they have to be the same variable carrying the same exponent. Woo, maybe I took this way too far, but long story short, people, when we are adding or subtracting, this does not simplify any further. All right. They're actually not like terms. So keep it the same way. All right, let's go ahead and do the first example problem after all this learning that we did. All right, simplify each expression. All right, let that sink in, look at it. And I want you to complete this. I know that the book gives you the steps, but I want you to complete this on paper. Okay, the way that I'm going to be writing down might be a slightly different way than the book does it. All right, I'm going to make sure that it flows. All right, so the first thing that I want to do is I want to expand this. I want to write it out in a way that you understand it a little bit better. There is no adding or subtracting here, meaning we don't have to do any distribution. All that I need to understand is that pretty much everything here is multiplying. The 3 is multiplying with the n to the 4th power, right? Then that is multiplying with 4, which is multiplying. And by the way, what I'm doing right now is something that we don't have to do all the time. This is just the first example, so your mind and your brain can see where it is that we're going to. After the first few examples, you're going to see how fast this becomes. What do we do now? Well, we can now take care of the numbers. We can actually do 3 times 4 first. We can actually reorder it because remember, in multiplication, the order of your multiplication doesn't matter. If you had 3 numbers multiplying together, 2 times 3 times 5, the order that you multiply this will not matter. You will always get the same answer. That is not the same idea with subtraction or division. It works with multiplication. So I can actually reorganize this. So 3 times 4 is going to happen. And then my n to the 4th power and n to the 7th power will multiply. So I can actually do 3 times 4, which is 12. That's a simple idea. And now this section is what we're learning today, right? That section is what we're learning today. What do you get when you have the same base and they're multiplying and, you have different exponents? Well, you pretty much are going to grab your base, keep it the same. 4 plus 7, that's going to give you 11. Ta-da! Your answer is 12 times n to the 11th power is the same thing as 12n to the 11th power. That's it. There is nothing else to it. Okay? There's nothing else to it. Now, is there a way that we can maybe speed this up a little bit more? Those of you that maybe thought that this was too confusing because there's too many steps. Well, let me see if I can simplify this a little bit more. Look at everything you have here. There's no adding or subtracting. There isn't. So you don't have to do a distributive property right now. Don't worry about that. What we do is focus on pretty much where are your numerical values. So your numerical values are going to be 7 and 2, right? You got 7 and 2. And then what we have here is we have x, y to the 2nd power. And let's already put them together. We have x on the first one, and we have another x to the 4th power. So let's get them on the same side. And then the y's, I'll go ahead and write the y to the 2nd power and then y to the 3rd power. Okay. So I didn't rewrite them like this in that same order. I actually just rewrote them where the terms that I want to put together are already kind of next to each other. All right. Here you could see 7 times 2. We can do that. These guys are like terms, and these guys have the same variable, which we can put together through multiplication. 7 times 2 is going to give us 14. X times x. What's x times x? Well, x times x is the same thing as saying x to the 2nd power. The most common mistake, listen to me right now, the most common mistake is people thinking that x times x, or something that looks like this, you guys are going to start confusing this with 2x. And that is not the case. That is not true. X times x is not 2x. X times x is x to the 2nd power. X plus x. This is 2x. Be careful, be careful, be careful. Continuing, we have y to the 2nd power and y to the 3rd power. Well, how many y's do we have in total that want to multiply? We have a total of 5 of them. 2 here, 3 here. So there's a total of 5 y's that want to multiply. And this is the simplest way that we can write that idea. Let's make sure we have it correct. 14x to the... Oh, whoopsie daisy. Well, did you not see that, Mr. Cranio? That 4 right here applies to the x. Hopefully you were screaming at the screen when you were doing this. I forgot about this little 4. I wasn't looking at it. This 4 right here applies to the x. So if we have 4 right here and we have 1 more right here, that is going to give me 5. Ay, ay, ay. All right. Good thing I checked. There we go. All right, let's do another. All right, so we just finished. Is there a little... Give me 1 second, because there should be a check problem. Let me get you guys your check problem. All right, never mind. I just looked at the book. There's no check problem for that first one. All right, so really quick, just to recap, we just learned how to simplify when we have the same base, right? When they're multiplying with the same base. And exponents, right? What do the exponents do? They add, right? Simple idea. Now, what are we looking at now? This next one is called a power of a power. I call it power to a power. All right. I call it a power to a power because what's going to happen is we're going to have something that already has an exponent. So if you look at what it's written there, it says a to the power of m, right? There's some number that is already has an exponent, or other books and places call it exponent, power to an exponent, or exponent to a power. It just has different names. I like to call it power to a power. So much simpler. When something's whatever number already has an exponent, and then they're giving it another exponent, right? And just remember, don't freak out. Exponent just means repetition of multiplication. So let's see what that looks like with the example. Example number 3. By the way, we did skip example number 2. We will get back to those after this video. All right. I'm making sure that we just do the actual algebraic process, and then we'll get to word problems later. All right, example number 3, power of a power, power to a power. Simplify each expression. So we got n to the 5th power, and then all of that to the power of 3. Now I'm going to give you a visual. One more time, I'm going to give you a visual to make sure you understand what it looks like. N to the 5th power just means this: 1, 2, 3, 4, 5. There are 5 n's that are multiplying inside of the parentheses. What does the power of 3 tell you? The power of 3 tells you that they want you to do that 3 more times. So they want you to multiply it. Remember, it's a repetition of multiplication. 1, 2, 3, 4, 5. All of them multiplying. This is not only happening twice, but it's happening a total of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is the visual. I just expanded what is being asked in the problem. Obviously, you can see that this is not something that we want to do over and over again. This is what I'm doing for the first problem and explaining it to you. Where is that everything comes from? So hopefully you can agree that all this right here is n to the 5th power. All this right here is also n to the 5th power. And this right here is n to the 5th power. Don't you see that my n to the 5th power, doesn't this make sense that I'm getting my groups of 5 n's that are multiplying and it's happening 3 times, right? So this should make sense. The n to the 5th power is happening 3 times. Do you see that? That's the same thing. So if you're wondering, is that the answer? No. Wait for the answer right now. Give me a second. The answer is as simple as this. You're going to go ahead and look to see how many n's are pretty much laid out. How many n's do we have? We got 5, 10, 15. So n to the 15th power is your final simplified, most simplified answer. What is the fastest way? Mr. Cranio, I don't want to do this. I don't want to expand all this. That's a lot of work because 5 and 3 are relatively low numbers. What happens if they're bigger numbers? That's a lot of work. Well, think about it. What does the 5 and the 3 do to become 15? If you go back here to the little the key concept, we are saying that whenever we have a power raised to a power, those values just multiply. So hopefully you said it before that we multiplied those two numbers. So yeah, let me erase this. This is the same thing as saying n to the 5th times, whoa, that's supposed to be a 3, which simplifies 15. That's it. Those are the 2 steps. If you're wondering how long this should take you, it's that long. Okay. And to the 15th. Part B. Pause it and try to see if you can get it. All right. Part B. Same idea. X to the 4th power is happening twice. You can expand it and look at it yourself, or you could see that x to the 4th power, we need to do a power times power, 4 times 2. That is going to give us x to the 8th power. If you need to expand it, so be it. Expand it out to see how many x's you're going to be writing down, right? In here, there are 4 x's, 4 of them that are multiplying. They want you to do that twice. Well, twice 4 is 8. So solution is x to the 8th power. Moving on. All right, check problem. Pause this, try it out. Don't cheat. All right. Now you can understand that expanding it is not such a good idea all the time. Imagine if I were to do 1, 2, 3, 4, right? N to the fourth power is pretty much this right here. That's n to the fourth power. Imagine if I were to do that 11 times. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's how many times I would have to write 4 n's. All right. So imagine that I had 4 n's, 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 11 times. What is the same idea? Well, think about what I just said. Imagine if I had 4 n's 11 times. There are 4 n's multiplying here, but I want to do that 11 times. That means that I have a total of 44 of them. Now, don't think of n, just don't. I know that I say 44 n's, but remember that these variables, these letters that they're giving us, they are going to be, right now they're unknown numbers, but later on we can find them and use them and plug in whatever number it is. So there it is. Our answer right here is going to be n to the 44th. All right, B, same idea. Whenever we have a power to a power. Another way that you can think of this is distribute this power into the other exponent. So what this is going to look like is going to be -7 times, and I'm just going to put it in parentheses because it's a negative times a negative, and that is what we're going to get. The answer is going to be 21, x to the 21th power. And yes, follow your multiplication rules. A negative times a negative is a positive. Cool. And how does that make sense? Why would it become a positive? Well, just think about a negative number being multiplied by itself, right? Repeatedly. If you think about the number 2, a -2, what do you get when you multiply it times a -2? You're going to get a negative times a negative becomes a positive. But then if you do it times another negative, your next answer is going to become negative. And then times a negative, your next answer is going to become a positive. So if you keep doing that an odd amount of times, right, you'll get to a positive solution at the end. All right, so we've covered 2 things from that introduction slide. We've talked about what happens when the same base is multiplying, right? And we have exponents. What do we do with the exponents? We simply add them. Those 2 exponents, we keep the same base and we simply add them. Also, what happens when we have a power to a power, when some number has an exponent, and then again, we have another exponent? Well, we simply multiply those 2 numbers, those 2 exponents, the power to a power. Now we're going to be looking at this one, which is called power of a product. A power of a product is, remember that product means multiplication. So something's going to be multiplying. All right, something's going to be multiplying inside of parentheses. And then that thing, so here is something, thing, sum. So something is going to be multiplying. So sum times thing. Something's going to be multiplying inside of parentheses. And then we're going to have some sort of exponent. I'll put the exponent of 7. So what do we do with that? Well, it's very simple. If you look at this, a times b, and all of that to the power of n, what you're going to see is a has its own power of m and b has its own power of m. So pretty much what we do here is just distribute it, give it to everybody. That's all we're doing. So let's get to it. I think the faster we get to the example problems, the quicker you understand it. Because sometimes I talk about it and it can be more confusing if I talk about it. All right, here it is, example number 4. So we have 3x to the 5th power. And y to the 2nd power, and all of that to the 5th power. What do we do here? Well, what we do here is this. Boom, boom, boom. I'm going to remind you once again, now that we're here in the 4th example, please complete these example problems on a piece of paper. I know that the book spoon feeds you too much. You need to have the repetition and the muscle memory. All right, complete all of these steps on a piece of paper. If you want to fill out the blanks in your book, so be it, but please do the repetition. All right, so what do we get here? Well, we're going to have 3 to the 5th power here, because if we're giving a 3 to the 5th, an exponent of 5, that's what it's going to look like. Simple as that. Now, this next one, what does it look like when I have an x to the 5th, right? I already have an x to the 5th, and they want me to take that another 5th power. Well, we already did this. We already learned this. This is called power to a power. A power to a power when you have an exponent raised to another exponent, what's happening is just those two exponents multiply. That's all that happens. So that right there is going to give us, and I'll go ahead and write it that way. I'll write it that way. So x to the 5th power, and I'll go ahead and introduce, you know what? Everything that I'm bringing in, it's going to be in red. And then we have a y to the 2nd power already. It's already got a 2nd power, but we're bringing it, or we're giving another exponent. So remember that a power to a power, you're multiplying it. So what does this become? Well, we already know that this is going to be 3 times 3 times 3 times 3 times 3, 5 times, right? And then this can be simplified as 25. 5 times 5 is 25. And then 2 times 5 is going to give us 10. We're almost done. What do you think we can do here? We can actually figure out what is 3 times 3 times 3 times 3 times 3. Now, you could sit here and do that math, but in algebra, you're supposed to already know how to do that. What I'm going to show you is how to use the calculator whenever the numbers become a lot larger, and it becomes a lot more trickier with that. So in this calculator over here, what you need to do is, if you want to find out what is 3 to the 5th power, you're going to type the number 3 first, type the number 3, and then you're going to tell the calculator that you are about to give the calculator some number for the exponent, and that is located right over here. This button right here is you telling the calculator, hey, I'm about to give you an exponent. As soon as you do 3 and then you click that exponent, you're going to click the number 5 because that's the exponent that you're giving the calculator. And what is that going to give you? Hopefully in your calculator, you got the number 243. All right, 243. And this should be your final answer. All right, that's our final answer. All right, let's go ahead and try B. Let's go ahead and try B. I'm going to do this a little bit faster, but with a little bit more flow and showing you how quick and easy this could be when you understand the concept. All right, here it is. All right, so we have parentheses and we have an exponent outside of parentheses. This reminds me that I want to distribute. Here it is. Distribute to everything inside. Everything inside. I'm distributing to the 5. I'm distributing to the A, and I'm distributing to the B. Everything inside gets a power of 2. So that 5 did not have an exponent, but now it does. What else do I have? I know that we're also multiplying by A. Well, don't freak out if I didn't put these little multiplications in between, because remember, when a number and a variable or two variables are right next to each other, we know that they're multiplying. So that A has no exponent. We understand that the exponent, if it's not there, is a 1. So let me go ahead and put that with the black ink. And then we just multiply 2, which, you know, common sense is just going to give us 2. We're also multiplying a B to the 4th power. So B already had a power of 4, but we're doing a power to a power. So we're raising an existing exponent to another power. And that's it. This is the way it looks like. What is -5 times -5? We can actually do that math. -5 times -5 is going to be positive 25. We continue with A. We keep the base, and we do 1 times 2, which goes to 2. And then B, keep the base. 4 times 2 becomes 8. That's it. There's nothing else for this answer. Check it out. Check it out. Hopefully you're getting a little bit more comfortable with this. Let's try a check problem. Pause it and try it. All right. Here we go. What am I going to get here? Well, I'm going to go ahead and distribute that 3. So this 4, I'm going to write it this way really quick, a little bit separated, the information that's already there. And then in the red, I'll go ahead and show the distribution of the 3 to the 4, to the X, and to the Y. I'll remind you guys that this right here is the biggest mistake. Students forget to give the exponents, like the 6 right here, they forget to give it to that first number right here. Everything gets it. Everything that's inside of the parentheses gets the exponent. So 4, which already had an exponent of a 1, because remember, if we don't see it, it's already a 1, because obviously there's already a 4 there. So we know it's 1. You get an exponent of a 3. So 3 times 3. And then that's -2 also gets an exponent of -3. There it is. So what do we get when we have 4 times 4 times 4? Now, remember that you're going to want to, if you have this calculator here, you're going to be typing 4 first. You're going to tell the calculator, I'm about to give you an exponent. And the exponent I want you to take it to is the number 3. What do we get here? We should get 64 x to the 9th power, because 3 times 3 is 9, and then y to the negative 6th power. Okay, y to the negative 6th power. That's it. That's the answer for that. That is the answer for that. Now, I'm going to give you a little bit of an intel. This is something that we're not going to learn later on. I'm sorry. This is something that we're going to learn later on, not right now. And the truth is that when we simplify something, we don't like to have negative exponents. We, for whoever the heck made these simplification rules, I don't want to, simplifying fractions. We don't like having, negative exponents. So the way to deal with a negative exponent is very simple. You take it to the other side of the fraction. What do you mean other side of the fraction? Well, imagine that all of this is just over 1. So if you want to take that exponent and make it positive, you grab that x to the 6th and you put it, y to the 6th, negative 6, and you put it at the bottom. And as soon as you put it at the bottom, as soon as you take this to the denominator like that, it's a positive. All right, it's the same thing as a positive. Now, I'm not going to go down the memory line and explain the whole thing because we're going to do that later, but just know that that happens. Now, hopefully you remember from that little first paragraph that we talked about in the second slide, a monomial or a polynomial, anything that's called a nomial, cannot have a division of a variable. So even though this is the answer, and this is also, the answer, this is not considered a monomial, okay? Because we have a division of a variable. Fun fact, keep it in your back pocket for when we get to that lesson. All right, next one. We're gonna have to distribute, and distribute, right? So we have a negative 3, which we're going to give a power of 6 to. We have an a, so an a that already has a negative 3 exponent, and a b that has a power of 1. We don't see it, but we know it's there. So we are giving the 3 a power of 6. We're giving this a also a power of 6, which already had a power of negative 3, but giving it another one. That's the math problem. All right, what is negative 3 times negative 3 times negative 3, right? All 6 times. That's going to give us 729. 729. What is negative 3 times 6? That's going to give us negative 18. And what is b? B to the first power times 6. It's going to be b to the 6th power. Now, once again, Corinne is going to give you a little side note that you can take it for later lessons. Remember that this is not called a binomial. It cannot be called a polynomial. The reason why is because if you want to write this simplified, fully simplified, you'll grab that a that has a negative exponent and you take it to the denominator. So now that you put it in the denominator, you have a positive exponent. That is the true way to simplify it. And now since we have a denominator of a variable, or we're dividing by a variable, this is not a monomial. This is not considered a monomial. But it's okay. Don't just kick it out and say, oh, we can't use it or it doesn't have any. No, it's just the way that we label stuff, right? Some of you guys are brothers, some of you guys are sisters, but it's just a title, it's just a name. All right, guys, you're going to be completing page 9, 1 through 18. I'm going to show you really quick the problems. So if you don't have the book, pause it whenever you need to pause this and copy the problems down. There you go. All right, stay tuned for the video solution for these problems. Peace out.